Hi there and welcome back to Calculus of Variations. This is video number 17. In the last video I derived the Jacobi accessory equation. Now I wanted to add a little section onto that just to clarify. I looked at the second variation, I2, the integral from a to b of, and I took out a common factor of eta x, of course that's epsilon squared upon 2 factorial. I took out a common factor of eta x, and then I was able to write this equation in the form of f00 eta minus d by dx of f01 all times eta minus d by dx of f11 times eta derivative. Okay, and that was all by dx. Now, in order to make that whole equation equal to 0, we know that eta is not equal to 0 because that's a small variation or small perturbation. So this thing here must equal 0. Okay, but in the previous derivation when I did Euler-Lagrange, we were able to take all the values of eta out of this and then use the fundamental lemma. But now in this instance, eta is still a function of this differential equation. Okay, so we could have a value of eta that would make this equal to 0, but our value for eta might not necessarily make this equal to 0. So what we can do is we can rewrite that. We can take out our Jacobi accessory equation, okay, and rather than using the term function eta, we could use a term u. Okay, that's u minus d by dx of f01 minus d by dx of f11. Okay, and that's u derivative. Okay, so we could find a function u that made this equal to 0. Now the function u may be the same function as eta x, but it might not necessarily be the same function as eta x. So eta x would make this equal to 0, not in all instances, okay, but in this here we're saying we'll pick a function u that that will allow us to make this equal to 0. Okay, so we do end up with two functions. We'll end up with a function eta of x and a function in u. Okay, I wanted to clarify that from the last video. Now, in this video, we're going to look at the Legendre test for weak extremum. Now, I've not talked about strong and weak variations, but I'll go on and talk about that in a different video. Okay, now from the roadmap that we talked about, we have two functions. Okay, we'll call that function 1, and we wanted the Jacobi accessory equation, which is function 2, and we said we were going to use function 2 in order to simplify function 1. Okay, now we'll write these down so that stuff becomes more apparent. If I put the first one down, okay, we have our second variation, we'll call it I2, equals epsilon squared upon 2 factorial, the integral from a to b of eta squared f naught naught plus 2 eta derivative f naught 1 plus eta derivative squared f11 all by dx, and we'll call that equation number 1. Now the Jacobi accessory equation was what we had above, so we could write that as u f naught naught minus d by dx f naught 1 minus d by dx of f11 times u derivative. Okay, now that's equation number 2. Okay, so we're going to do some manipulations with these equations. Okay, and I can show you quite quickly what it is we're looking to do. We're trying to find the sign of this term here. Okay, is it positive or is it negative? Okay, but we're trying to simplify this in order to find it. So what we can do is we can get rid of these terms here and replace them by only the one term here, and you can see how we're going to do that here, because we're going to set that, I should actually say equal to 0. Okay, that equal to 0, so we've got in this here we've got 0 0 and 0 1 here. Okay, 0 0 and 0 1. Right, so we can take this, we say that equals that there, so we can replace this here into, so we can place this here in here for these terms. Okay, now we'll only have a term in f11, and we can simplify it in such a way that we can ensure that we have an f11 and the value of f11, whether it's positive or negative, will wholly determine the value of the entire function and whether the entire function is plus, positive or negative. Okay, now let me continue and we'll see if we can get these in the right format. Now I can write this I2 here, and we've already done some of this, but I'll quickly go through again as a reminder. I can write that I2 as epsilon squared upon 2 factorial, the integral from a to b. Now I can leave the first term as it was. Okay, I'll put it down so you can see it. The first term as it was, eta squared f naught naught. Okay, now the second term here, we know, because we've done it previously, that we can write 2 eta derivative is the same as saying d by dx of eta squared. Now we know that because if you differentiate that out, it's implicit differentiation, so you would have 2 eta times the eta by dx would equal 2 eta derivative, which is what we've got there. Okay, so I'll just rub these out because I don't want all this cluttering that up. Okay, so now we would have, instead of that there, we would have d by dx of eta squared times the f naught 1. Okay, now I can use integration by parts in order to make f naught 1, I should be clear about that, that's there. Okay, I can make f naught 1 the subject of the differentiation, and I can take the n squared out. Okay, now again, I've talked before about integration by parts, and I've put a little video on the snippet section, so quite quickly you can look at this and you can do 3 steps. You can make that a negative sign. You can take the n squared out, eta squared I should say, eta squared out, and make d by dx, make f not 1 the subject of the integration. Okay, so I'll just rub that out. And again, look at the integration by parts video, or just in previous videos, you'll see that I've done that and how quickly it can be done. Okay, so that's second term there, and we can also write our third term. Bring it up. We can write our third term, that eta derivative squared f11 can actually be written in the form of minus eta d by dx, eta derivative f11, okay, but the whole thing by dx, by dx. Now again, I've done that one previously, and we know that this here equals that there, because if I went through and did integration by parts on this function here, this function here, I would end up with this function here as well. Okay, so again, you just work through it yourself and you'll see, and I actually did it in the last video as well. So there's my rubber, get rid of that. Okay, so that can be written in that form. Okay, now let's now look at, if we take this here, okay, and we look at that there. I'll just write it below. We could write that u of f00 minus d by dx. Okay, now I'll take this across to the other side. Oh, f0 d by dx of f01. f01. Okay, I'll take this across to the other side, equals d by dx of f11 u derivative. Okay, now what I'll do is I'll take the u down on the other side as well. Okay, so we'll get rid of that u there. Okay, and we can make that 1 upon u. Now this is the whole reason for deriving this, for us to derive this Jacobi excessive equation, or for using it, so we can write this in the terms of f11 only. Okay, so that means that I can rewrite equation as I2 equals epsilon squared upon 2 factorial, the integral from a to b. Now I'll just write it out, and then after I've written it out, you can see when I multiply the terms out how I got them. Okay, so I can write that out as eta upon u, okay, times eta d by dx of f11, and I'll just write it as du by dx, okay, minus u d by dx of f11 right d eta by dx. Okay, and of course that's all by dx. Now you can see how I got that there. If you were to multiply that eta by eta, you would have a eta squared. Okay, so we would have a eta squared term there. That's the eta squared there. Okay, and let's see, getting this right. Sorry. So we're coming in here. Sorry, we're coming in here, and we're using this here. Okay, so we're replacing our values here. Okay, so that's what we're replacing. We're replacing this here in the first instance, these two here. Right, so we're replacing these two here with this here. Okay, so we need an eta squared, so that's eta and eta, we'd have our eta squared. Okay, and f naught naught d by dx f naught 1, okay, becomes d by dx f11 u derivative 1 upon u. Okay, so that's our 1 upon u section there for this here. Okay, so that's the first term being replaced, and the second term we would just need a value of eta and this here. Okay, and that's what we've got. We've got a value of eta, right? Because if we are learning, we put our u upon u, those will cancel out, and we'll simply have our value of eta d by dx f11 d eta by dx. Okay, now just sit and look at that and convince yourself that that's right. Okay, and you'll see quite quickly that is actually the case. So now the next step that we can do is we can then write that whole thing out as epsilon squared upon 2 factorial integral from a to b. Now here's another, I'll write it out and then explain it. N upon u, okay, d by dx of f11 n u derivative minus u n derivative. Okay, there's a bracket for that one there, that there, all by dx. Now you might look at that and say, well, how I was able to, because what I've done there is, if you look at the top line to that line, I've taken that eta inside that differential, I've taken that u inside that differential. Okay, so the both of them, eta is going inside the differential and u is going inside that differential. So you say, how do I know, how am I able to take these inside that differential? Well, if you were to use the product rule for differentiation, so if you were to take that's one missing there, isn't there? Actually, that's f, no, that's okay, it's f11 times, yeah, times a whole lot of that. Okay, okay, so if you were to do the product rule for differentiation, you would have 3 terms in a product minus another 3 terms in a product. Okay, so if you work that out, you would end up with those 6 terms. Okay, okay, it'd be like doing the product A, B, C derivative. That's what we've got here, a product of as a differential, and there's a 3 terms here minus 3 terms. So to do that, it would be A derivative B times C plus A B derivative times C plus A B C derivative. Okay, so we're doing that, but we're doing it twice. We're doing it for a positive value and also a negative value. Okay, so when you work through these and you differentiate them out and you gather like terms and subtract them off, you'll find out that this line here is exactly the same as the line above here. Okay, you're able to take these values eta and u inside the differential. I have worked through it, and I sat and worked through it just the other night there, and it does work. Okay, so I suggest you go ahead and try that yourself. I'm just not going to put it in because it's just well, it's cumbersome, tiresome, and you can just work through it yourself anyway. Okay, so we've got that line there. Well, hopefully I can keep going with it. making any big boobs. Okay, so we're in that factor there. Okay, now that again, if we use integration by parts, okay, then it will allow us to take this term here out of the differential. Okay, so it means we can get this f11 outside the differential, and then this n upon u goes back in. Okay, so it means that we're putting something simple inside the differential and taking something complex out of it. Okay, so, and again, I'm not going to go through all of the process integration by parts, but we could end up with I2 equals epsilon squared upon 2 factorial, okay, and it's the integral from a to b. Now, differentiation by parts, the three things we do, we make a negative sign, so we'll take a negative sign there. Well, there we go. We'll put the negative right outside there. Okay, and we will bring what's inside the differential outside. So we'll have f11 nu derivative minus un derivative. Okay, and what was outside the differential now comes inside the differential. So that would be d by dx n upon u, okay, all by dx. Okay, now we can rewrite that again. I2 is minus epsilon squared upon 2 factorial integral from a to b of f11 eta u derivative minus u eta derivative. Now, if you remember your differentiation here of a quotient, I'll just write it down below. If it was d by dx of eta upon u equals eta derivative of u minus eta u derivative all upon u squared. Okay, so now I'll replace this here with this term here. Okay, so that would just then become eta derivative of u minus eta u derivative, okay, upon u squared, and I'll get rid of this here, just getting in the way. Now, not long to go, just another couple of manipulations, and we'll be able to get this in the right format. Okay, so now if I multiply the whole structure and then gather like terms, we have minus epsilon squared upon 2 factorial integral from a to b, and it's f11. Now bring u derivative out here, sorry, u squared. Now I multiply these out along hand, so it will be n u derivative times n derivative u minus n u derivative times n u derivative minus u, if I say n, it should be eta derivative times eta derivative u, and the final term would be the plus term, would be u eta derivative times eta u derivative all by dx. Okay, so multiply the whole lot out. Finally, gathering our terms together, we could write that as I2 equals, and we can get rid of the negative sign there by changing the negative signs in there, so we'd have epsilon squared upon 2 factorial integral from a to b of f1111 upon u squared. Okay, and that would be, I'll just write it out there, so it would be when we make the negative, and we obviously that's eta squared u squared, so I'll write that out there. It would be eta derivative squared u squared minus 2 eta derivative u derivative plus eta squared u derivative squared all by dx, and that can be written as only 2 lines to go, and that's as I2 equals integral from a to b of epsilon squared upon 2 factorial of f11. Okay, and we can take the u in, so it's eta derivative squared minus 2 eta derivative u derivative upon u plus eta squared u derivative squared upon u squared all by dx. And the reason for doing that is the final line is that we've completed the square, so we can then write that as I2 equals epsilon squared upon 2 factorial the integral from a to b of f11, and that's eta derivative minus eta u derivative upon u all squared by dx. Okay, so everything we've done so far is to get to this point here. Now, the reason why I want to get to that point here now is we're interested in the sign of this. Well, irrespective of what we choose for epsilon, epsilon is squared. Okay, so that's always positive. Okay, the value 2 is positive as well. Now, if we if this term here obviously is squared, okay, so that term there is either equal to 0, okay, or greater than 0. So we can say eta derivative minus eta u derivative upon u squared has got to be greater than or equal to 0 because it's a squared term. Okay, so now if we say that it is so if we say initially we say it's greater than 0, we won't look at the equality term. Okay, that's another video. But if we say that term there is greater than 0, then the only term that determines the sign of this whole thing is this here. Okay, that's positive, that's positive, that's positive. Therefore, this here, the sign of this determines the value of that, the sign of this. Okay, so that was the whole reason for doing it. It means we can say that if, in this instance here, if we can say that if this eta derivative minus eta u derivative upon u is, okay, if we say that that is doesn't equal 0. Okay, so if we say it doesn't equal 0, right, and if we say the other proviso, I suppose would be, the other proviso is that if f11 doesn't change sign, it doesn't change its sign over the interval AB, okay, so that's the integral of the derivation of the interval of the over which we're deriving the functional, then we can say that if I've just squeezed it in here, actually that's 1, 2, we can say then that if f11 is greater than 0, then we will have a weak minimum. Okay, we have a weak minimum. Okay, and if f11, oh, it's just a phone going there, ignore it. F11 is less than 0, we will have a weak maximum. Okay, thanks for listening to this video, and I'll get you on the next video. Okay, bye bye.